Hi, here's a presentation for the priority queues. For this project, I collaborated with Houston and Bridget to debug one of the tests. The bug is I should have updated HashMap before swimming the nodes in the heap. For HeapMinPQ, we're using the Java implementation of PriorityQueue. So after this for loop, this diagram would be the accurate representation of state of testing. So we first add string 1 with priority 1, then we prioritize left subtree, then we focus on completing the tree, so 3 with priority 3, and then we just go left to right, so 4, 5, and 6. For the code tracing, we're changing the priority of element 3 from 3 to 0. In my changePriority method, I'm traversing the entire heap list to see if there's any node that contains the target element. And utilizing the fact that two priority nodes objects are only considered equal if and only if their element fields are equal. That means that we can ignore checking priority value in this line. So we start with the top of the heap, which is 1, and it doesn't equal to 3. And we go to 2, it doesn't equal to 3. Finally, we have element 3 equals to element 3. So we enter this if condition. We call pq.removeNode. This is a Java implementation of this method. So what it's doing is it will swap the current node with the rightmost node, which is 6, and then it will delete 3, the target nodes, and then we add it back. We add the element 3 with updated priority. And then since this breaks the invariance of the heap, behind the scene it will swim the 3 up to 6 by swapping, and then it will swap with 1 because 0 is more priority than 1. Similarly, when we change the priority of element 1 to be 7, we first remove it from the heap. That means it will swap with 6 and then get deleted. Then we'll reinsert it with the updated priority. There's no need to heapify because 7 is greater than 6. For the assertions, let's consider the case when we change the priority of element 3 to 1. So for double map implementation, aka the reference, the main priority will be 1, and then the elements with main priority will be derived from the tree map. So we're adding element 3 to the set under priority 1. And because we are only returning first of this set, so what we call remove min, it still returns element 1. And then for HeapMinPQ, aka the testing, if we add the 3 under 1 with the same priority level, it doesn't heapify because we only swim the node if its priority is smaller than its parents. Remove min also returns element 1. And if reference is storing element 1 with priority 8, and then testing is storing element 1 with priority 7, this test should still pass because the two objects are only considered equal by their elements. The priority values are not checked for equality. Previously, for HeapMinPQ, we are the client, and now we're the implementer using an array list. To do this, we first ignore index 0 to allow easy calculations, and then we insert element 1 with priority 1 to index 1. And then we store this information in this hash map called elements to index. So we have element 1 with index 1. Then we do element 2 with priority 2 here, and then we store the index in respect to its element. So we continue doing this until we have all the elements. For the change priority method, we first do check if our heap contains element 3. So we'll go to elements to index HashMap and see if its ksets contains element 3. Then we'll grab the index and then use that index to get the priority node from the array list. Connecting back to the diagram, we use the key element 3 to get the index so that we can retrieve this priority node from the array list. Before we update the priority to be 0, we need to store the old priority so we can make the comparison below. This is used to maintain the heap invariant, so in this case, the new priority is less than the old priority, so we will swim the priority node 3. We're passing 3 as k, and then we will compare if k divided by 2 is greater than k. For the method greater, we will check if the priority node at index 1 would have a bigger priority value than the priority node at index 3. In this case, 1 is greater than 0, so we return true. We then exchange the two nodes, so this is just storing the nodes, and then we set index 1 to have element 3, and then we set index 3 to have element 1. We also need to update the hash map to ensure we're getting the right index. Element 1 will have an index 3, and then element 3 will have an index 1. Next, we will change the priority of element 1 from 1 to 7. We first use the hash map to grab the index for priority node 1. We store the old priority 1, and then we set it to be 7. And since 7 is not less than 1, we will sync the node to restore the heap invariant. For the sync method, we pass in k equals to 3, so j equals to 6. This line is to ensure that we're only exchanging with the minimum child, but we can ignore that because we only have one child. And because the priority at index 3, which is 7, is greater than the priority at index 6, we'll exchange the two nodes. So 1 will be here and 6 will be here. And it will modify the hash map to be like this. For the assertions, both the reference and testing rely on heap property, which ensures that the elements with the minimum priority is always at the root. For the double map, we use the minimum priority to get a set of elements, and we only retrieve the first element from the set. For the OptimizedMinPQ, we get the priority node at index 1, which is guaranteed to have the minimum priority value. And then we do a bunch of stuff to restore the heap invariance. Again, the test will still pass because we only check elements for equality, not priority values. For the unsorted array, there's no best case because the node with minimum priority can be at any index. So we always loop the entire array list, which is dependent on the size of the array. Therefore, remove min and change priority both have theta of n as runtime. For the HeapMinPQ, the worst case is when we swap the root with the rightmost leaf, we sync the new root all the way down to the bottom level. Remove min method's worst case runtime will be theta of log n because Java util.PriorityQueue has O of log n for poll and an O of constant for peak. For change priority, the worst case is when the target element is at the bottom of priority queue. Java implementation has O of log n for add and O of n for removing object. So the final worst case would be theta of n. For optimized HeapMinPQ, the worst case is when the new root sinks to the bottom of the heap. The remove min worst case runtime would be theta of log n, the reason being the exchange method, which uses a hash map, runs in constant time. Removing last in the array list also runs in constant time. Finally, for sync method, it runs in O of log n with the height of the heap. Then for change priority, the worst case is if the change node sync or swim the maximum amount of times. So it traverses all the way across the heap. The worst case would be theta of log n because all of these lines, which includes hash map lookups and priority updates, are all constant time. Only the swim and sync runs in O of log n and they're not nested. Finally, for DoubleMapMinPQ, the worst case for remove min is when all the elements have min priority. So they're all stored in the elements with min priority tree sets, which is a left-leaning rev-like tree. We need to traverse all the left nodes in order to find the min. The worst case will be theta of log n. The justification is that tree sets use left-leaning rev-like tree. So both the first key and get methods traverse the leftmost nodes with worst height O of log n. All the other operations are hash table based, so they are O of constant. Finally, for change priority, the worst case is when all the elements have the same priority. So we need to traverse n elements in order to find the target. The worst case will be theta of log n. If we look at the code, elements with O priority is a tree set, so remove element has O of log n in worst case. Priority to element is a tree map, so remove key also has O of log n. Finally, add method also have O of log n because it uses methods like get in tree map. So if we combine them, the worst case will be theta of log n. For the last durable, the tree bucket optimization has no impact on the asymptotic analysis because we assume that the hash map in reference and optimized HeapMinPQ both have hash functions that evenly distribute the element across the bucket. In our asymptotic analysis, we didn't consider collisions at all, so we didn't consider a worst case where all the elements are in the same bucket, forming a linked list. So we never have to convert a linked list into a rev-like tree. The majority of operations are either constant or theta of log n.